In previous tutorials, we learned how to load our qPCR data into the application and define the experimental conditions of our analysis. Now it is time to get familiar with the settings of the analysis, and this tutorial teaches us how to configure any setting of the application from the Analysis Profile tool and how these configurations affect the analysis. Analysis Profile is organized in 6 main steps of StatMiner qPCR analysis: management of technical and biological replicates, detectability flags, delta CT normalization, and finally, differential expression and cluster analysis. So, starting with the CT quality section. A technical replicate represents the same sample and detector, duplicated several times, mainly to assess the technical precision of the technology. These replicates are supposed to have similar CT values, and StatMiner is able to test whether this happens or not by detecting potential outliers amongst the replicates. 2 methods are available to do this: grubs and CT fraction tests, grubs being the default method. Although both methods work in a similar way by comparing each value with the median of the replicates, CT fraction is considered more stringent for low CT values, as higher values are supposed to differ from the median. Basically, selecting grubs will lower this p-value threshold, thereby relaxing this evaluation, meaning that there is a lesser probability of getting outliers. On the other hand, CT fraction threshold represents the percentage distance of the value from the median. In this case, a higher distance is what relaxes this evaluation. Finally, if the automatic removal is checked, StatMiner will proceed to detect outliers and remove them before aggregating replicates left using the summarizing method indicated on this combo. So, how can we inspect the technical replicates that have been considered outliers? First of all, StatMiner notifies the number of outliers detected in the whole experiment from the information panel of the CT quality step. With more detail, this chart shows the CT distribution of the technical replicates for each detector and sample. For instance, these are the 3 technical replicates of this cerebellum sample for this detector. Red values indicate the presence of an outlier. In this example, we can identify some different scenarios where this reference control has replicates with very similar values. This is the expected behavior. Another one which has not been replicated at all. 3 replicates per samples. Outliers are represented in red. And finally, 2 replicates where no outliers have been detected, since we need at least 3 values to determine an outlier. Coming back to the analysis profile, qualification settings describe how the application deals with the sample outlier detection and the imputation of missing values. In a similar way to the technical replicates detection, the application detects outliers in the correlation of samples belonging to the same biological group. It means that StatMiner is able to automatically compare the CT values of samples within the same group and notify us if any sample is extremely different. Biological replicates are supposed to have similar behaviors. The higher we set this parameter, the more relaxed will be the test that we use to find these potential outliers. Just to reiterate, these samples would be removed from the analysis if automatic removal is checked. On the biological replication report, we can check those samples that have been detected as outliers and confirm the similarities between samples by inspecting the correlation plot. Red values indicate that samples have a good correlation, that is, when the CTs behave similarly, but blue values mean that samples are poorly correlated. As expected, samples within the same biological group will have a good correlation. In this example, the first reference sample is an exception, and that is why StatMiner is notifying this event in the information panel. Regarding the second qualification section on imputation, and to maximize power in a statistical analysis, StatMiner gives us the chance of replacing missing CT values by an aggregated new CT value taken from the identical detector in the same biological group, and this is the method we want to use to generate this imputed CT value. Let's continue with the detectability settings. It is important to know that no actions or data have been modified by these settings. The target of these quality values is just to notify us about the detectors that have a very low level of expression and to help us decide whether we can trust the biological results being reported for the differential expression analysis. In short, this parameter defines a CT threshold where all CTs above it will be flagged. According to this value, one biological group will be flagged for a certain detector if the percentage of flagged biological replicates is greater than the given threshold. All this information will be later reflected in almost all the differential expression reports, so we will have the chance to determine whether we can rely on these comparisons. As we can see, the reports use a color legend to highlight if we have detected inefficiencies in the amplification of target, control, or both biological groups. We will continue this tutorial by talking about the normalization settings section. These sections are mainly focused on how we want to select the reference detectors that we will use to normalize our data. It is common to use a combination of reference controls to calculate delta CT values, but in case we haven't got any or the analysis consists on a large set of detectors, it is recommended to use all targets to normalize the data. In the first case, StatMiner gives us the option of using all reference controls or 3 different methods to test and define a subset of best reference controls. In the second case, we will use all target detectors. In any case, the application creates a new profile with the normalization factors to be used on delta CT computation. As far as these options work on the endogenous controls, we can use this tool to define a set of reference genes by just moving the set of targets to the endogenous control one. If we have chosen one of the automatic selections to determine the best controls, we can inspect the scoring method selection and the new profile of the normalization factors once the analysis has been done. As we can see, these are the candidates to create the normalization profile. In this case, they are selected by NormFinder scoring method. This is the profile as a result of aggregating 2 controls regardless of the summarizing method, and these are the controls discarded by NormFinder since they were not considered stable enough. A reference control is supposed to have an acceptable stability along biological groups. Targets will be normalized by subtracting this virtual endogenous profile. Let's go back to the analysis profile. In this section, we can define the aggregation method to create the normalization factor profile we have just mentioned. Endogenous controls can be removed by default from the differential expression analysis, but if we want to keep them, we can check this option and they will be normalized and included in the expression analysis. Finally, there is a way to test if our controls are good enough to normalize our data. StatMiner will compare the stability of hundreds of targets taken randomly with available controls and let us know via information panel if our controls are stable enough or whether it is better to normalize data using the global expression level option. We finished this tutorial with the last section of the analysis profile where we can tell StatMiner the type of expression and classification analysis we want to perform. This is just the configuration of an initial analysis, and once click and go execution is done, we can iterate over the statistical analysis as many times as needed, specifying different types of comparisons and cluster classifications. We recommend getting further details on the differential expression and clustering analysis tutorial. But as a whole overview, these sections allow us to define the groups to be compared using a parametric or non-parametric test. Regarding clustering, StatMiner can perform the classification of the normalized and RQ values. In both cases, we can define what to do with the missing values, as well as the method to generate the cluster tree and how to estimate the similarities between the delta CT and RQ values. In case our data comes from a different experiment, it is recommended to perform a previous normalization so we are able to compare the data. That's all. We can now finish by saving our selection so that we can use the same configuration on subsequent analysis. As we can see, StatMiner already provides 3 predefined configurations for a default stringency that we may want to apply to the analysis. We have now loaded our data into the application, defined the experimental conditions, as well as specified the settings of our analysis. We are now ready to execute a qPCR analysis. We recommend that you watch differential expression tutorial to get further details of how to interpret these reports after a click and go execution.